questions if there are any, but because my first lecture was just a couple of hours ago, maybe there are not many questions, and I will try to cover some more ground. This is a privilege for handling the first tutorial. So, I referred to a point of view expressed by Sommerfeld, and it seemed a little surprising to some of you possibly. So, he describes many simple mechanical systems as examples in which there are constraint forces. He calls them reactions. What I was calling constraint forces are called reactions in this book. And then he says, we now expand what we have learned with the help of the above examples into a general postulate. In any mechanical system, the work of the reactions equals 0. This is what I said. Constraint forces do not do any work. So, you can invent lot of examples and convince yourself that it is true. Then he goes on to say, far be it from us to want to give a general proof of this postulate. And then there is a footnote. It is very interesting. Lagrange attempts this, that is the proof of this as a postulate, in the introduction of his Mécanique analytique, which was written in 1788. And he says, attempts this in the introduction of his book by means of certain block and tackle constructions. So, it is 240 years ago. So, it tells you the mentality at that time, and it reinforces what Kelvin said 112 years later. To understand anything in physics means to make a mechanical model of it. So, you see how far we have gone. So, then Sommerfeld goes back. So, far be it from us to want to give a general proof, rather we regard it as definition of a mechanical system. Okay, so, I will take that attitude. Okay. Then you can build up the whole formalism of classical mechanics. One can always ask, what if there is a physical system which does not obey this condition? We just have to take the attitude, every such situation has to be handled separately on its own. You develop certain general methods and skills based on a restricted system of examples, those which obey the Sommerfeld condition. So, you learn how to develop equations, descriptions on those in those situations. Then the idea is you have learnt enough about the way to use mathematics in any given physical situation to handle cases where this condition is not obeyed. So, that is left to the reader. If you are interested in a situation where Sommerfeld's condition is not obeyed, it is your responsibility to find out how to handle it. Okay. So, there is no point in setting up a general formalism to handle all cases. So, please take that attitude. So, there is no answer to the question, what if in a particular system this condition that constraint forces do no work is not obeyed. It is your problem. take that attitude, but you must have learnt enough mathematical machinery to be able to handle it on your own. That is the attitude everybody takes. So, this is, so I have returned the book to you. Also, I wanted to mention, I showed Shamik, this typed version of my lectures are available in soft copy. So, in a few, in the tea break, I will probably forward it to him and you can see how to use it. So, let me just ask if you have any questions which can be answered on general grounds. If they are very specialized questions, I leave the answer to you. Any questions about today morning's material? Yeah.
Somewhere I have read best inertial reference frame is cosmic wave, microwave background.
Yeah.
What it means?
See, that is a very subtle matter. I don't know the subject. There is someone here who has worked in cosmology Oh, your most recent physics faculty member. Yeah, he might know. Thing is that there is a very well-known person in TIFR by name Unnikrishnan. Many of you may have heard of him. Some of you may have seen him. It's impossible to miss him if you see him. He's a wonderful person, very independent thinker. He has worked on this problem. He has written about it in some of his commentary type articles in Current Science a few years ago. See, the frame in which the cosmic microwave background appears isotropic, it's not just called an inertial frame, it's called a preferred frame as far as I know. If you were to move with respect to that, the isotropy will be lost. So, it is not helping you to define an inertial frame, but a special preferred frame, and that is quite hard to understand on the basis of, let us say, special relativity. Normal relativity, Galilean or Einsteinian, says there are inertial frames in nature. If you have one inertial frame and somebody is moving uniformly with respect to it, that is also an inertial frame. This is the general foundation in both kinds of mechanics. Once you come to general relativity, the description of gravitation as geometry of space-time, the situation changes. The idea of an inertial frame becomes a local idea. It's not a global idea. So, you do not have global inertial frames in the framework of special relativity. So, I think the questions are very subtle. It will be going too far from mine to try and answer it. But you read this article of Unnikrishnan. I don't remember the title, but it was 4 or 5 years ago, and he will give you many other references also. Okay. So, it looks like in nature there is a preferred frame, the frame in which the cosmic microwave background radiation appears isotropic. That is my understanding. If that is so, the idea of inertial frames goes down the drain, right? But you have to accept it. It means that it has made the already general relativity had said the Newtonian or special relativistic idea of global inertial frames definable everywhere, that has to be given up. Already it is gone. So, it remains as a local idea. On top of it, you bring in the experimental fact that there is a cosmic microwave background radiation, it alters the situation even further. So, I will just leave it at that. Okay? All right. Any other question? I take, yeah? Physically, they are there, and in the equations which I call Lagrange's equations of the first kind, there are terms involving those Lagrange multipliers. They are explicit expressions for the constraint forces. It is not a question of physically what is the use. They are there, you cannot avoid them if there are constraints. Okay? I mean, just suppose you say that you have this small object moving on the top of the table. The idea physically is, if it were to try and get off the table, you will push it down. So, something will keep acting on it to make sure it obeys the constraint. It is there in one form of the Lagrange equations of motion. You get explicit expressions for the constraint forces, but you can then ask this question, which will lead me to my next topic. Out of the Newtonian equations of motion, in which constraint forces are also there, how can you get all the consequences in which the constraint forces do not appear? It is not that you are removing them or abolishing them, you are asking for the part of the information of the full equations of motion in which they do not appear. That is what leads to the Lagrangian equations of the second kind. So, I think I will start on that, and since also these lecture notes typed version may come to you quite soon, what I am going to do is not give too many derivations. I will indicate this ideas and then tell you where you must put in some effort to supply the missing steps. Okay. So, let me start in this way, recapitulate the arguments. The Newtonian equations of motion using Cartesian coordinates have the standard form, Newton's second law, for each particle in an n particle system. And we have said that in case there are constraints, the total force acting on each particle is made up of two parts. One part which I denote by capital X, and which is even Sommerfeld's book describes it in this way: the part of the force F which has known physical origins. For example, forces exerted on particle J by particles K, L, M and so on, they will come in X. These are called applied forces with known physical origin, and they are called applied, and they are given forces. The C's are the remaining part of the total force, the force which is needed in order to see that the constraint is always satisfied. These forces are, in Sommerfeld's language, called reactions. I call them constraint forces. They are of geometrical origin, unlike the X's which are of physical origin. For example, physical origin, gravitation, electrostatic force, things like that. They are things which appear in capital X. The reaction forces are of geometrical origin because they have to be there in order that the constraints get satisfied. They are not generally known in advance. Depending on the problem, you have to work out. If you want to know what the constraint forces are, it is part of your problem to compute them. They are not given in advance, unlike the capital X's. So, this is the main thing. And in the Lagrange equations of the first kind, which I displayed on the board this morning with those Lagrange multipliers, formally that is a way of giving you an expression for each of these forces. Okay. But now the spirit of the analysis is different. The idea now is, out of these Newtonian equations of motion, we know some information about these constraint forces, namely what Sommerfeld called the idea of definition of a mechanical system. What we know is that, well, we imagine that there are a set of constraints on the Cartesian coordinate variables. They are given to you, and the fact, physical fact, is what I am writing now. The work done by the constraint part of the forces in any actual movement, actual or virtual, which obeys the constraints, the work done by this part of the force is 0. So, here is a very well defined mathematical problem. Here is a complete set of equations of motion involving true physical forces and constraint or geometrical origin forces. Here are the limitations you place on the coordinates. The X's are not all independent. Here is a physical fact which, as Sommerfeld says, can be checked by you in a variety of examples. And once you have seen all the examples, you say, I will assume this is always true in my discussion. That, as he says, he will take this condition to be the definition of a mechanical system. Okay. So, as I said earlier, if you say, I have a situation where this is not true, what shall I do? I say, go home and do some mathematics, use all that you have learnt and create some more mathematics to handle your situation. Okay. That is the attitude, and it is a reasonable attitude. So, then the well defined question is the following: given the full equation of motion, given the constraints, and given this property of the constraints, what are all the consequences of these equations of motion in which the Cj do not appear at all? What can you write down which is a consequence of Newton's equations with the property that in those consequences the C's just disappear? How can they disappear? Only because of this condition. This is the only property you are given. Okay, so this is the idea. And so then, as I said in the morning, let me get my papers right. You assume that it is possible to choose generalized coordinates q, and their number I have told you in the morning. It is by notation, the q's are listed in this way. These are the generalized coordinates, and you choose them in such a way independent of one another, so that every Cartesian variable can be regarded as a function of the generalized coordinates, and this representation of each x guarantees that the constraints will always be obeyed. That is the main thing. Next is, if that is true, then you, in the actual motion or in a virtual motion, whichever you like, the changes that occur in the Cartesian variables are not all independent of one another. They have to have this form, obviously. Every allowed variation of the Cartesian variables is the result of a variation of the generalized coordinates. Each generalized coordinate can be varied independently, but each x cannot be varied independently. That is the idea of the constraint. Then I will give you a let me just get this right. Yeah, sorry, sometimes I use it, sometimes I don't. Here I don't use it. Here I do use it. It should be clear from context. Okay. Here it is used. Summation convention is used. So allowed variations of the x Cartesian variables are only of this kind, where each delta q can be chosen independently of every other delta q. That is one thing. Second, it is only such variations which you should consider during the physical motion, and it is only if delta x has this form is this physical fact valid. The work done by the reaction forces is 0 along any motion as long as the constraints are always obeyed. Now, I would like to leave this as a sorry, I have written it with too many deltas here. Cartesian velocities are related to generalized velocities in this obvious way, and there are simple elementary consequences of these equations which I will not go into. So what you now do is take the Newtonian equations of motion, multiply both sides by an allowed delta x, both sides, and sum over j. So what does it become? I make the following claim. I write this equation. I take the Newtonian equations of motion. I multiply both sides by a delta x of this form. Okay, I put it on the left and I put it on the right. Now you see that this term drops out. That was this condition, this property of constraint functions. And in this statement, since the q's are mutually independent, we are permitted to drop delta qr. each generalized coordinate can be varied all by itself, others not changing. They are independent of one another. So, this is the key equation. You can write it down, you can derive it at leisure, but here is the physical meaning of this equation. This set of equations, how many equations do we have? One for every generalized coordinate. The only free index in this equation is r. It goes over the different generalized coordinates. The physical statement is the fact that this captures that part of the Newtonian equations of motion in which the constraint forces do not appear. That is the main thing. So, this is a subset of, it's a part of the information contained in the Newtonian equations of motion, but it is that part in which you never see the constraint forces. It does not mean constraint forces are 0, but this is that part of Newtonian dynamics in which you can forget about them. So, the whole idea is how far can you go and what can you say if you are not interested in the constraint part. Now, so this is one of the equations in my notes. Since you will soon get them, I will write it with a number, and the number of these equations is exactly equal to the number of generalized coordinates. Okay. Now, I will tell you some properties of the left hand side and properties of the right hand side. I will not derive those properties. That will be a very interesting exercise. If this tutorial had been tomorrow rather than today, then I would have left this as a problem for you to solve by tomorrow. In any case, I will tell you what you have to try to prove, and I will ask you to try it between now and tomorrow. The two properties I want you to try and establish for yourself are the following. Left hand side of 15 with a series of simple mathematical operations. This is what Lagrange accomplished in his great book. It is called Mécanique Céleste in French, published in 1788. It is, I have not read that book. I don't know how many people today would have read it, but I believe people like Sommerfeld when they say this is what he did. It turns out the left hand side, this thing can be rewritten in a very interesting form. I will write it, I will not give you the derivation. Left hand side of equation 15 carries an index r, which labels the generalized coordinates. So, there is free index r here. T, it is a function of generalized coordinates and velocities. It is the kinetic energy of the n particle system. Rewritten in, start with the Cartesian form for it and rewrite it in terms of the generalized q's and q dots. So, the fact that the left hand side takes up this form is really remarkable. Of course, it is 240 years old, so we should all be used to it by now, but if you haven't done the derivation, please try it or see any book where it is given. The main thing is this is the kinetic energy, the sum of half mv squared for every particle in the system summed over all the particles. When it is written in terms of q and q dot, because it is a non-relativistic situation, this kinetic energy expression is quadratic in q dot. Okay? So, that is something physically important. As I said in the morning, many of these developments of Lagrange, Hamilton, Jacobi were all in the background of Galilean Newtonian relativity, non-relativistic physics. The amazing thing is that that approach extends to all other situations also, but this is how it was originally done. Huh? All Q's, more importantly all Q dots. Yeah, the generalized velocities, where are they? It will depend on all of them. In fact, for a genuine non-relativistic system, it will be a what you may call a non-degenerate quadratic expression in Q dot. It will involve every Q dot, and it will involve, so if you like in more detail, it for non-relativistic systems, it necessarily has to have this form, because it has to be quadratic in Q dot, and the coefficients of Qr dot Qs dot may be Q dependent, and this has to be non-singular, and what else? Real, of course, positive definite as well, because this is positive definite. So, for non-relativistic system of particles, all this can be said. This quantity T which appears in this expression is necessarily of this form, non-degenerate or real positive definite expression, quadratic in Q dots. Q may occur in the coefficients. Okay. So, this is as far as you can go for the left hand side. Then the question is, what is the right hand side of 15? This part. This, it turns out, also can be written in a nice form. I will put it in this way. Left hand side of right hand side of 15 equals coefficient of the variation delta Q r in the expression for the total work done by all the external given physical forces capital X in a small change in the configuration of the system. And this is usually written as delta W, the infinitesimal work done. The symbol delta W is used. Now, the delta Q's are the only independently variable infinitesimal quantities. Delta X's depend on delta Q's. So, this as a matter of definition is written as capital Q. Well, for the moment, let me just write capital Q dependent on the generalized coordinates. So, this is called the generalized force rth component, one for every independent generalized coordinate. So, then you take the left hand side, the right hand side, equate them, and here is the, well, I first write it and then I describe it. You have one equation of this form for each generalized coordinate. So, remember, this is a treatment of non-relativistic systems of point particles. So, capital T is that kinetic energy, but you have made full use of all the given constraints and written kinetic energy as a function of Q and Q dot, and it has the form I just rubbed out, positive definite quadratic form in Q dot. Capital Q on the right hand side is the generalized force which is obtained by writing the work done in an infinitesimal displacement in terms of the generalized coordinates. So, capital Q is introduced in that way. This is called, this system of equations is called the Lagrangian equations of the second kind. In the first kind, which we saw in the morning, there was that second term with the Lagrange multipliers. Those terms were the constraint forces. But we are now asking, what are the consequences of Newton's equations in which the constraint forces don't appear? These are the consequences. This is the content of the equations of motion in which you have completely eliminated the forces C, the reaction forces. So, this is the real Lagrangian system of equations which we study and develop much further. Okay. So, I have left some things for you to convince yourself, to show that the left hand side of this equation 15 can be manipulated into this very special kind of form in which the kinetic energy plays a role. And remember, as I repeated, this is assuming non-relativistic kinematics. But the thing is that when special relativity replaced Galilean relativity, mechanics had to be changed, expression for kinetic energy had to be changed, square root expressions came. In spite of all that, the general principles of Lagrangian mechanics survive. And when you go to electromagnetic systems, electromagnetic fields, field theory, again the Lagrangian methods survive. The connections to non-relativistic mechanics disappear, but the existence of a Lagrangian, all those things, and the possibility to write equations in this form, that remains. So, this is the part that you have to hang on to. So, let me now define what is called the conservative case, and that is what we will most of the time deal with. The conservative case is as it is defined in ordinary potential mechanical problems involving a potential, is the case where the work done in an infinitesimal displacement can be regarded as a change in a single function, a potential function V of q. So, that is a definition of the conservative case. Let me just, I lost my page number. There must be a minus sign somewhere here. A system, mechanical system, is said to be conservative if these generalized forces which appear in the Lagrangian equations of the second kind have the form, each capital Q is the negative of the derivative of some one function with respect to the corresponding variable. Okay. Once you make this assumption that you are dealing with a conservative system, things simplify a great deal. You put this into the right hand side, take the right hand side, move it to the left, and you see very easily that the equations of motion have the following form. You define a single function L of q and q dot, it is a kinetic energy minus this V, and all the equations of motion can be written in a very compact way in this form. So, that is the case for a conservative system. These are now called the Euler-Lagrange equations of motion, because Euler had done some work which is related to this final form. So, let me remind you of some of these standard terminologies. L is called the Lagrangian of the system, and these, and it is a function in general of q and q dot, and these are the complete set of equations of motion obtained after getting rid of the constraint forces. That is the main point. And now we make this a guidance for all later work in mechanics. I will say it in words and you will appreciate. So, let me just write it with its arguments. It is a function of q and q dot. This is the basis for all the discussion to come. So, you have to imagine you have some physical system with n degrees of freedom, number of independent generalized coordinates. Then you choose in some way the q variables, q1, q2 up to qn. So, each one of them will have some physical meaning which can be measured, and each one of them will have a certain range in which it can vary continuously. Then their time derivatives will be the generalized velocities. So, you can say this part is the kinematic description of the system. What are the variables you use to describe different configurations of the system? What is the nature of each q? Is it an angle? Is it a length? Is it something else? It can be anything. But each generalized coordinate must have a well defined physical meaning. It must have a well defined range of values which it can take, and typically these are continuous variables. And then you say the physical system is completely defined for us once a certain function of q and q dot is given to you and you are told this is the Lagrangian for my system. Once the Lagrangian is given for a system, chosen or discovered, whatever you like, its dynamics, its equations of motion have this standard form. So, you see the beauty of this Lagrangian description. All the differential equations for all the independent coordinates, they are all contained in one single function. In other words, in the Lagrangian point of view, from the physical equations of motion aspect, everything is determined by one given function. You tell me what the Lagrangian is, I know how to go ahead and write out its equations of motion. This is the, in the Lagrangian language, the most refined form of Newtonian equations of motion. Okay? So, the only condition that you should place on a Lagrangian, I mean, can you choose any function you like as a Lagrangian of a physical system? It is a subtle question. It is not possible to choose anything you like. Of course, the previous discussion was based on non-relativistic particle systems, but you now generalize it. Say, you may choose any, well, first decide how many degrees of freedom you have. Second, you decide what are the independent generalized coordinates, what is the physical meaning of each one of them. All taken together, they describe the configuration of your system at each instant of time. Their time derivatives are the velocities. Then, are you allowed to choose any function at all of q and q dot and say, this is my physical system and these are the equations of motion? The answer is yes, provided this set of equations does not lead to any inconsistency. Now, you might wonder, why can there be any inconsistency? Why can't I choose any Lagrangian, any function of q and q dot and decide that is my physical system? Well, the importance of this was brought out by Dirac in his theory of constraint systems, which I described last year, a year ago. It is a very simple example. Dirac gives this example for 1 degree of freedom. Can you choose the Lagrangian for 1 degree, 1 q and its q dot? Can you say, I want to choose this as my Lagrangian? What does this equation become if L is equal to Q? What is this term? 0. So, what is this term? What is this term? 1. It's not allowed. So, if you read Dirac's paper on constraint systems, he says a Lagrangian is permitted to be chosen as the Lagrangian of a physical system, provided from these equations you cannot draw the conclusion 0 equals 1. This is the way in which it is written. Please see this. Dirac's, I gave the reference last year. It is a lectures on quantum mechanics given in Yeshiva University in 1964. It's a beautiful set of 60, 80 odd pages. It is freely available on the internet. These are his words. A system of a Lagrangian is physically allowed or permitted, provided you cannot conclude from this set of equations, you cannot draw the conclusion 1 equals 0. That's the way he puts it, just his way of saying it. So, I am just emphasizing it to say you have complete enormous freedom in the choice of a Lagrangian, provided the equations of motion it gives rise to do not lead to mathematical inconsistencies by algebra. That is the main point. Okay. So, now I will stop this second lecture it has become, but I will stop it very soon with just a few comments which will put things. Yeah, some.
So I have a question.
Yeah.
This generalized force, it has no dependence on the velocity, by definition.
No, at this stage here, because we thought of this expression depending only on coordinates. But I am coming to many generalizations. First of all, this whole machinery works perfectly well even if you have no constraints. The original Lagrangian Newtonian equations of motion for a conservative system. I will write the Lagrangian and you will see. You take the original Cartesian description of a system of n point masses, you take as your Lagrangian the normal expression for the ordinary kinetic, non-relativistic kinetic energy, you assume it is a conservative system, subtract some potential V of x. Work out the Euler-Lagrange equations written here for such a Lagrangian. They will be just the Newtonian equations in Cartesian variables. This is just to say that the formalism gives back the known results in the limit when there are no constraints. Okay? Only assumption made is that it is a conservative system. That is the first point. Second point, you can generalize it to allow for velocity dependence in these things, in the generalized forces. In that case, this V which you subtract, it may have also a q dot dependence. The generalization is permitted by this formalism. So, these are the ways in which you can go beyond the original derivation, and as you know, every one of them has been successfully done. You can imagine the most general functional form for the Lagrangian. Again, for the case of special relativity, free particle in special relativity, what is the Lagrangian? It depends only in Cartesian variables. This is the Lagrangian for a free relativistic particle. It will give you free motion in special relativity. There is, however, a restriction here that the speed must not exceed the speed of light. But I only want you to realize this Lagrangian is not of this quadratic in velocities form. It is not non-relativistic, it is fully relativistic. See, a square root has come. So, it just shows you that you can extend it in various ways, this formalism, so that you can describe physical situations which were not originally thought of in this formalism. So, you have a restricted set of physical situations, get a result valid for all of them, and then you find the results can be applied much more widely. That is what you have to, they are not limited to where they were derived from. Lastly, there is a case of the electromagnetic field. That one again I will leave it as a, I think I will take it up tomorrow. I will show you the equation, the expression for the Lagrangian when you have a charged particle, let us say non-relativistic, moving in an external electromagnetic field. What is the Lagrangian for that? There you will find q dot dependence in capital Q, velocity dependent potential. Okay? That will be shown. Now, I will conclude with what I may call the covariance group of the Lagrangian form of mechanics. So, this introduces some group theoretical terminology. It is a useful thing to know, and the physical meaning is extremely simple. So, what is the meaning of this phrase? Covariance group of the Lagrangian equations of motion. The idea is very, very simple. Where did we get the Lagrangian form of mechanics in the first place? We said you have some constraints obeyed by the Cartesian variables. Therefore, you introduce a smaller number of generalized coordinates so that all of these are automatically obeyed. And the choice of the generalized coordinates, no other condition. It must be something which obeys the constraints, otherwise it is completely free. So, supposing you have a situation where you have one set of coordinates, generalized coordinates, and another set q prime equally able to satisfy all the constraint conditions, then you can develop the Lagrangian system on this description, or you can do it in the other description. So, what is the most general relationship between them? There must be rules of transformation from generalized coordinate q to q prime, and it must be possible to go in the opposite direction also. So, the meaning of this covariance group is the following. I will just write it as a statement, and then I will leave it to you to verify that this is true. This is the complete equations system of equations of motion in the description based on generalized coordinates q with a corresponding Lagrangian. Now, this Lagrangian is a function of q and q dot. Now, the statement is the content of the first set of equations is the same as the content of what I am now writing, where the new Lagrangian, a function of the new variables, is the same as the old Lagrangian in terms of the old variables. The statement is, beyond saying that the constraints have to be obeyed, nobody told you how to choose q. So, if you made one choice and Shamik makes a different choice, every q prime he chooses is some peculiar function of every q. Provided it is consistent with the constraint conditions, nobody can stand in the way of his choice. This is, by words, it is a proof that the content of all the equations of motion in one description must be the same as the content of all the equations of motion in any other description. You are perfectly free to change your choice of generalized coordinates in any Lagrangian description. That is the point. Number has to be the same. Why? Because in the original derivation, this number of constraints was given. And what is this remaining number of q's? 3n minus this number. So the number of degrees of freedom cannot change. But the way you describe the configuration of the system, you have infinite amount of flexibility. Okay? So this is what is meant by the covariance group of the Lagrangian equations of motion. So now going back to what I said earlier, a system with a certain number of degrees of freedom has to be described by a certain set of independent generalized coordinates. Each one of them must have a clear-cut physical meaning. And each one you must know what are the allowed physical values. If it is a Cartesian type of position, it can go minus to plus infinity. If it's a radial variable, 0 to infinity. If it is an angular, maybe 0 to 2 pi and so on. But you can start with one description and at any point switch to another. The new q primes, each one will have a physical meaning, but q prime 1 may not be the same physically as q1. Q prime 2 can differ from q2. Each one must be well defined. That is the main thing. Okay? And therefore, there must be a set of equations which tell you, if I know q, I know q prime. If I know q prime, I can go back to q. So that is where the group property comes in. And the covariance idea is just this, that the content of the equations of motion are the same whether you describe it in one system of variables or another. Okay? So this is a very general and important idea. I think I stop at this point, and we can stop the tutorial also at this point, unless there is some pressing question. Yeah. So. Yeah, please. Yeah, go ahead.
So this Lagrangian equations, they can also be derived from the principle of least action. So
that I am coming to as a.
no, so from the historical perspective, like which one preceded?
Yeah, Lagrange's equations came much before the principle. See, the principle of least action is a complicated and tortuous story. Just to tell you a little bit, you will read it in Sommerfeld's book. One of the first persons, see, in optics there was already this Fermat's principle of least travel time of light, sort of inspired by that a French aristocrat Louis de Maupertuis. He stated a principle of least something or other for mechanical motions, for mechanical systems. But it is said that he was vague in the way he stated it, and there was no proof that was given by him, no credible proof. So initially, and this is given in the Sommerfeld book, initially what Mr. Euler and Mr. Lagrange did independently was to sharpen the statement of Maupertuis' principle and give some kind of proof for it. Then this idea of an action principle, principle of least minimum action, the idea persisted because it was so appealing. And I think the ideas of theology were mixed in with it. That is how it developed. And Hamilton gave the most useful form of the principle of least action around 1835, 1840, in that period. That is the form that has been used ever since, and that is what all of us learn. There are many other minimum principles. There is a Gauss's principle, there is a Hertz's principle, there is a third fellow's principle, Jacobi's principle. All of them have same spirit, but nothing as clear-cut and easy to use as Hamilton's principle. And so that is what is normally taught. That is what I will show. So it's a nice point you raised, again very interesting historical fact. For mechanics, for dynamics, it was the equations of motion which were first discovered by Newton in all its glory. putting it into the form of a variational principle went through all this 150 years, Maupertuis, Euler, Lagrange, Gauss, so many people, ending with Hamilton. And his is the finest form, which I will describe later. Then you come to Maxwell's equations for electromagnetism. They came out of experiment, as I said. Who are all the people? Ampere and Faraday and Ørsted, and so all these people. Maxwell put all of them together, and the equations of electromagnetic theory were first discovered as a system of partial differential equations. They were shown to come from an action principle somewhat later, 40 years later. You must have heard of this man, Larmor, of Larmor precession. Yes. I believe that he was the one who first put it into the form of an action principle. That's very interesting, that it came first, that is, the experimentally observed phenomena were rewritten in the form of differential equations by Maxwell. It was only later, part of the theoretical development, it was shown that it can be thought of as a variational principle. Same thing happened with general relativity. The field equations, the equations of motion for general relativity in Einstein's theory, were first constructed by him in 1915 as a system of partial differential equations. Those are called the field equations of relativity. It turned out that the mathematician David Hilbert was very closely following what Einstein was doing. I believe there was a 7 days or 10 days time gap between Einstein and Hilbert, and Hilbert showed that the Einstein field equations can be obtained from a variational principle. There was a Lagrangian behind it. But his approach was purely as a mathematician. He did not have any of the physical insight which Einstein had into the nature of gravitation, the equivalence principle, and so on and so forth. So, the action principle for general relativity is called the Hilbert-Einstein action. So, in all these examples, what I want to stress is that the fundamental laws were discovered as systems of differential equations, ordinary or partial, first. It was later that it was shown that they can be derived from a principle of least action, some kind of variational principle. It was true in ordinary mechanics, it was true in electromagnetism, it has been true in relativity also. Only thing is the time gap has been much smaller in the later and later developments. So, I stop here, and what I want to describe tomorrow is this very beautiful Hamilton's principle, which leads to the Lagrangian equations of motion. So, I think that's enough for today. Yeah.
Can we write Lagrangian for subatomic particles like gluons, quarks, neutrinos?
Yeah, I told you in the morning, the idea of defining a physical system by saying this is its Lagrangian, it has survived till today. Only thing is, in the systems you are talking about, you deal with quantum fields, not particles as such, not positions and velocities of particles, but quantum fields which are like the electromagnetic field defined on space time. Okay. Now, when you write Maxwell's classical electrodynamics in the language of Lagrangians, the Q, what are the Q variables for electromagnetism? Do you know? I will tell you, but do you know? No. Exactly. It is the electric field and the vector potential together, which play a very important role in putting Maxwell's equations of electromagnetism into the framework of Lagrangian mechanics. I think this shows you once more how powerful or widely applicable this Lagrangian point of view was. He has succeeded far beyond anything he could have imagined. Just see the derivation, non-relativistic particle system, and now it works for field systems, for gravitation, general relativity, special relativity, even for the Dirac equation. People will ask, what is its Lagrangian? Dirac discovered his equation as a system of partial differential equations. Very soon it was found Yeah, you can write a Lagrangian for it. So, for quarks, leptons, gauge fields, they all have to be treated using methods of quantum mechanics, more precisely quantum field theory. So, for any one of them, the question you ask is, what is the Lagrangian to describe the quantum chromodynamics, the physics of quarks and gauge fields and leptons? What is the Lagrangian for the electroweak theory of Glashow, Salam and Weinberg? So, the idea of a physical interaction being completely described by a Lagrangian, that has survived for 250 years. That is really already quite amazing. That there has, even it surprises me also in the sense, nothing more has been needed to describe what is found in nature beyond the framework of Lagrangian ideas. Okay? But the variables which you use, they differ from case to case. I think that is really enough. Yeah, okay.
Definition also will change. If it is kinetic minus.
Yeah, so that was the starting point. But as I told you, it generalizes. You can write a Lagrangian for a relativistic particle. You can write a Lagrangian for electromagnetic field. You can write it for gravitational field in the language of special relativity. Of course, lot of special features come in each case, but the basic principle that a physical system, a force of nature, can be described by a certain Lagrangian, that has survived. That still guides our thinking. That is, huh?
Lagrangian in the sense a single function can.
Yeah, one function. What variables are inside it depends on the situation, but the existence, being able to describe it by one function, that is really remarkable. Yeah, yeah.
The starting of all that generalized coordinate, it has to have some physical meaning.
Yeah, yeah.
So,
Yeah.
is there any we can't choose any arbitrary generalized coordinate that?
No, you can, but when you make your choice, what's your name? Huh? Indrayud. So, Indrayud coordinate number 1. In your mind, it must be clear what you mean by your first coordinate. You must have a clear understanding what you are choosing. What is the physical meaning of your second coordinate, third, and so on. What I mean is, in the choice and meaning of every generalized coordinate, you should not allow confusion. You must not write Q1, Q2 and say, but I don't know what they are. Don't do that. So, all I am saying is, there is mathematics here, there is physics equal, we should say more important for us. Huh? Sure, each one can have its, huh? Sure, sure, they can be, angles are dimensionless. So, any choice is allowed, provided it describes your system faithfully and provided the user knows the meaning of what he or she is using. That is what I mean. You should not say, I have introduced some generalized coordinate Q1, Q2, but I don't know what they are. That is not permitted. That's all I am saying. Okay.
But it depends on the system I choose and the way I want its dynamics to be.
Yes and no. All questions, all important questions cannot be answered unilaterally. For a given physical system, as I said in the morning, suppose you have a system with spherical symmetry, single particle motion in a potential, then it would be really stupid to try and describe it using Cartesian variables. It is natural to use spherical polar variables, right? So, but the Lagrangian does not care. What your system of variables you use does not matter. Each choice must be well defined physically. Once you have made a choice, Lagrangian has a certain shape. You change your choice, L will change to L prime. But the equations of motion, the content of this collection of equations is the same as the content of this collection of equations. I am not saying that the first equation in this set is the same as the first equation in this set. No such thing. But the set of all equations written on the right and the set written on the left, total content is the same. So that answers your question. You have complete freedom in what variables you like to use. If some variables make calculations more easy, please use it. Okay. Yeah.
So in your example, spherically symmetric.
Yeah, yeah.
If we choose spherical polar,
Yeah.
the degrees of freedom becomes 2 or
So,
pi.
beg your pardon?
Degrees of freedom becomes 2 or
No.
the pi is constant. That's all.
No. The
Spherically symmetric system, if you want to describe,
Yeah.
r and theta are so
there, yeah, but the full description involves r, theta, and phi. If you had a Cartesian description, you have x, y, and z. If you switch variables, you put in r, theta, and phi. Do not omit phi. You must have full 3 variables in the new description, so that every one of the original x, y, z can be recovered, right? So you don't say it has become 2 degrees of freedom. No. Yeah.
automatically get rid of pi.
Not rid of. Phi has its own equation of motion. It may be trivial. It just shows that for that problem, the description r, theta, phi is much simpler. It's the right thing to do. It doesn't say you are eliminating a degree of freedom. Please don't make that conclusion. That's all I'm saying. The number of degrees of freedom does not change when you change the description. Okay? That's all I want to say. Yeah. You wanted to say something?
About that, didn't mention it.
Yeah.
Virtual displacement, it's somewhere here, right?
Yeah. Virtual display. See, suppose, it is a little bit confusing to read the literature. You please read the Sommerfeld book as carefully as you can. All right, and it will be hidden there. But the idea is the following. Suppose you have a given system of constraints. By definition, they have to be obeyed at all times. All right. So as the mechanical system moves, its coordinates change, its velocities change, at all times this must be satisfied. So it means that the changes in coordinates delta q cannot be chosen arbitrarily, delta x. They must be chosen such that this is always true. So from the physical point of view, the constraints are always satisfied, and the physically occurring changes delta x1, delta x2, etc., will always respect the constraints. Now, what is a virtual displacement? What I just described is a actual displacement. How much does x1 change in time delta t? How much does x2 change? Those are actual changes taking place during the motion. But you can imagine, without thinking of development in time, I have one configuration given by x1, x2 up to x3n, and I have a nearby configuration x1 plus delta x1, x2 plus delta x2 up to x3n plus delta x3n. I am not thinking of equations of motion. Are both of them such that the phi equations are satisfied? If so, you will say it's a virtual displacement, an imagined change which respects the given constraints. That is called a virtual thing. Right? What is virtual reality after all? Something you imagine, whether it is there or not, right? But something which does not violate laws of logic and consistency. That is all that we have to be careful about. Yeah. I think I cannot stand here anymore. I am tired, so I think it's enough. I've covered a good amount of material, so I will catch up tomorrow. Okay then, thanks. No clapping. Okay. Yeah. So we can go to that room. Yeah. What is the time?
20 minutes.
You want to show me that room?
Sure.
Yeah.
Sir, can you think of third configuration which is consistent